All right, grade 11s, percentage composition, percentage yield. That is our title of our session for this day today. Okay, can't really say this evening because you might be looking at this recording in the morning or afternoon, whenever, or a couple of days from now. It doesn't really matter. Okay, but that's what we're doing today. And we're going to start off firstly with percentage yield. Now, there's two things that we need to have a look at first. One, there is terms such as empirical formula versus molecular formula. Okay, up until now, what we have learnt and what we know is molecular formula. Okay, now we're going to discover what in the world is this empirical formula. Okay, so empirical formula, if you just come down here, okay, this is basically empirical formula of a compound indicates what is known as the simplest, okay, ration or ratio, right, in which the elements, or in which elements of the compound, or that compound, have joined. Okay, just rolling with the definition now quickly. Come over here this side, take a bit of a lighter green. The molecular formula of the compound may be I'm going to say maybe a multiple. Okay, coming back to the molecular formula. Molecular formula of a compound may be a multiple of the empirical formula. Okay, so it might be a multiple of the empirical formula. And basically, for example, if we have, and we use another color, if we have benzene, okay, benzene is a real substance that exists, okay, benzene, okay, now the empirical formula, okay, is CH, but the molecular formula, in terms about how we actually write it, how we actually find it, is C6H6. So if we divide this whole thing by 6, we get the simplest ratio, which is 1:1. Okay, so the simplest ratio would be the empirical formula, and obviously the molecular formula is the formula in which the substance actually exists, C6H6. Okay, so that is the two, or the differences between the two formulae. Okay, now when it comes to percentage composition of a compound, okay, it can be calculated using the chemical formula of the compound. All right, and the relative atomic masses of the various elements which makes up the substance. Conversely, all right, the empirical formula of a compound can also be calculated if the percentage composition of that compound is known. What we're going to do is we're going to take a little bit of a young example here. Okay, we're going to take a little bit of a young example about how we're actually going to calculate this and work this out. Okay, so if they say determine, and I'm going to use kind of shorthand notation or shorthand writing here, determine the percentage, we all know that's the sign for the percentage of water, all right, percentage of water of crystallization. We all know what crystallization is, okay? Let me just get my eye properly, there we go. Crystallization in copper sulfate crystals. Okay, so in copper sulfate crystals we'll have some water in there, and the formula for that would be in a different color, CuSO4.5H2O. all right, fantastic. Let's leave it at that. Let's have a look at the solution. Okay, that's the question. Remember, this is just an example, so I'll do the solution for you. So the first things first is first, how on earth are we going to find out what's going on here? We need to first have a look at the molar mass of this bad boy. So the molar mass of CuSO4.5H2O rather. Okay, don't worry much about this dot right now. Okay, basically we know copper 63,5 molar mass plus sulfur is 32. All right, plus 4 times 16, which I think is 64. Yes, it is. Okay, and now we plus 5, because of the 5 here, times, well, that's 2 hydrogen, so that's 2, and 16 is 18, so 5 times 18. Okay, we're not worried about this dot. It's not math, so it's not basically a multiplication sign. No, it's not. Okay, so we find out that the molar mass of this entire compound is 249.5 units grams per mole. Okay, hope you all can see that there. Okay, so now we want to find the percentage of water. Okay, so the percentage of water, don't have to write the word, we can use the symbol. Percentage of water crystallization would be, well, what's 5 times 18? That's 90. So this entire number over here, which is 90, divided by the total, which is 249.5, and that would equal, all right, about 36. Oh, obviously you got to times by 100 over 1 to get percentage. That would equal roughly about 36%. Okay, so the actual figure, 249.5 times 100, is about 36,072. We'll give it in whole number, so 36%. All right, and that's just one of the examples of percentage composition. I do have another example, and I'm going to show it to you in just a moment. So have a look at a second example. They say now that there's a mass of a certain compound. Okay, there's now a mass of a certain compound. Okay, that is made up, and I'm obviously leaving out some words here, of about 30.4% of nitrogen. This is a more common percentage composition question. About, I can still fit that number in here, 69.6% of oxygen. Okay, and they say, first of all, number 1, determine empirical formula. So I'll leave it, determine empirical. And then number 2, determine the molecular formula. Okay, determine the molecular formula if the molar mass is equal to 92 grams per mole. Okay, so we're going to provide a solution for the first one first. Obviously, makes sense. All right, solution for the first one. They say a mass of a certain compound, okay? So there's more than one substance here. It's made up of 30.4% nitrogen and 69.6% oxygen. How many substances are here? Only 2, all right? Only 2 substances, nitrogen as well as oxygen, okay? So that's cool, all right? So now what we got to do is from the above information, we basically know when it comes to mass, we assume like percentage is 100%. All right. So therefore, we assume if they've given the masses in percentage, we therefore assume that for mass 100 grams of a substance. Okay. We usually go about just up until 100 grams of a substance. So therefore, we assume that 30.4% is equal to 30.4 grams out of 100 grams of a substance. Okay, so in a 100 grams of a compound, there must be about 30.4 grams of nitrogen, all right, and about 69.6 grams of oxygen out of 100 grams. Okay, that's what we know and that's what we assume. Now, from that, we can determine the following. Okay, I'm going to have to take some this away though. From that, we can determine the following. First of all, we know that it's 30.4% of nitrogen, so 30.4 grams. So what we want to come here and have a look at the moles of nitrogen in 100 grams of a substance of the compound is equal to, of course, the number of moles is N. So we just take the equal signs away here. N is equal to 30,4 all over the molar mass of nitrogen, which is 14, and that's equal to 2,2 mole. We do the same now of oxygen, 100 grams. N is equal to 69, oh, I have sneezed. 69,6 divided by the molar mass of oxygen, which is 16. And that gives us about 4,4 mole. Okay, stick with me for this for now. Okay, now we can see just by this. Okay, just by this, if we have a look at the ratio here, the ratio of nitrogen to oxygen is 1:2, because if we must half 4,4 divide that by 2, we'll get the top answer here, which is 2,2. So if we must equate these to each other, 2,2 to 4,4, divide them by 2,2 each, we'll get a ratio of 1:2. So in another color, blue, therefore the empirical formula for answer, or for question number 1, the empirical formula of the compound is N for nitrogen, which is 1, O for oxygen, and that's 2, so NO2, which obviously looks like nitrogen dioxide. Okay, that's for number 1, which was determine the empirical formula, and that's how we start, or that's how we begin to analyze and begin to find out the empirical formula, by assuming that these percentages are out of 100 grams. So we turn them into mass. So 30,4%, 30,4 grams. The second question was determine the molecular formula of the compound if the molar mass of the compound is 92 grams. So the molar mass is equal to 92 grams per mole. And basically this over here is the molecular formula's molar mass. This is the molecular formula's molar mass. Okay, so what we need to do is find out, well, what is our molar mass of the empirical formula? NO2. Well, that's 14 for nitrogen plus NO2, so that's 2 times 16 for oxygen. That's 32 plus 14, that looks like give me 46 grams per mole. Alright, now that I know that, since the molar mass of the compound, the molecular formula's compound is 92 grams per mole, okay, which is double the mass of the empirical formula. So this is double that. Okay, if you double this, you'll get that. Okay, so the molecular formula of the compound then must be double the ratio that I have here. Okay, so double the ratio that I have here would be 2 times this entire subscripts. So therefore we can say the molecular formula okay, of the compound is or the molecular formula must be of the compound N. So if this is double that, so multiply everything by 2 because 2 is doubling, so it's definitely N2O4. Okay, N2O4 is the molecular formula, and if we're interested to find out maybe what is the name of that substance, okay, N2O4, okay, which is basically it's not D-nitrogen, but dinitrogen tetroxide. Dinitrogen tetroxide, okay, which is basically referred to, or commonly referred to, as nitrogen tetroxide, and it is, let's see what is, it's used in chemical synthesis. Sorry, I struggled to say that word. It is used in chemical synthesis. Okay, if you would like to know further about what the substance does, you're more than welcome to have a look at it up on a YouTube video, or look at it up on the internet, and you're more than welcome to check what it does in YouTube, what it's used for, etc., etc. Okay, cool. Dinitrogen tetroxide, or commonly known as, I'll write down the name here, just nitrogen tetroxide. Alright, always interesting to figure out or know, alright, what the substances or these substances are. Percentage yield, similar to percentage composition. Okay, percentage yield, the maximum quantity of a product that can be obtained from a chemical reaction. Okay, now what do we call that? Okay, what do we call what I just read now? The maximum quantity. Okay, the maximum quantity of product, okay, that can be obtained from a chemical reaction. Okay, that is called, okay, theoretical yield. The maximum quantity, okay, may not be the actual quantity that you get, but the maximum quantity, okay, that is called theoretical yield. Means according to the calculations, according to theory, based on what we have here, without the reaction taking place, we should get the following, but that's not necessarily the case. Okay, in practice, there is invariably some waste in the isolation and in the purification of products. In other words, there are sometimes substance that goes not missing, but that is lost during the chemical process. Okay, and then we get something that is called the quantity of product. Okay, quantity of product, which is actually, okay, let's focus on that word, actually, all right, obtained in the laboratory while looking at the experiment, or while the reaction is taking place, or at the chemical plant, whatever, okay, is called actual yield. And then we put together a formula for percentage yield, which we write, and I'm going to write actually in another color, which we can just write it percentage, the percentage sign, and the word yield is equal to the actual yield, in other words, what we actually get, all divided by what we should have got theoretically. So by the theoretical yield. Okay, yield. Awesome. Okay, and then we multiply that, of course, by 100. Okay, cool. So that's the formula for it. It doesn't get really much more difficult than that. Okay, but the best way to have a look at this is obviously through an example. I just want to give you some time to get down those two definitions, and then we can go ahead and have a look at a example, and then have a look at an exercise. Okay. So in the example, let's say there's a laboratory experiment that actually really exists. Ammonia gas will be produced and collected using a certain apparatus. Obviously, we know in practice that we've come through, if we were going to use that, we'd use a glass jar with a delivery tube and a test tube. We'd put the certain substance in, like calcium hydroxide powder and ammonium chloride powder, mix it together, and then burn the test tube with a Bunsen burner. And then a reaction we'd get, if we just have a look at this example, the reaction that we would obviously get would be CaOH, which is the calcium hydroxide. Okay, that reacts with ammonium chloride. I know I said ammonia chloride, I actually meant ammonium chloride, NH4Cl. Okay, and keep in mind, just make some space there, these are all solids. Okay, because they're powder, they're not in liquid form, so they're considered solid. Okay, what you get is you get calcium chloride plus ammonia gas. So there's 2 ammonia gas there, NH3 gas plus 2H2O, and there's also a 2 in front there as well. Cool. And that's a perfectly balanced equation there. Okay. So when the mixture was heated, obviously we got that reaction from the Bunsen burner. Now, they say that the mass of calcium hydroxide, let's write our information at the bottom here, somewhere in the left, on the right-hand side here. The mass of Ca brackets OH, calcium hydroxide 2, was 40 grams. Okay. It is found that only 21 decimeters cubed of pure ammonia was produced. So that's a volume there of ammonia gas, NH3. Only 21 decimeters cubed. Okay. Assume that this volume is measured at STP. So at STP, standard temperature pressure. Calculate the percentage yield. Right, now before we all panic and go into complete pandemonium, alright, first things first that we always start most of these questions with is, what is the molar mass? Alright, so they say that what they've given us is the mass of calcium hydroxide. So if they've given us the mass of calcium hydroxide, guys, shouldn't it be wise to perhaps start working with this substance? So the first thing we do is we find out the molar mass of calcium hydroxide. Alright, what is the molar mass of calcium hydroxide? Well, its calcium is 40 plus, because of the 2 subscript at the bottom there, OH is 16 plus 1, so that's technically 17. 2 times 17, that gives us a molar mass of about 70 grams per mole. Now, as I said earlier, they've given us the mass in grams of the substance. So shouldn't we calculate the number of moles? Number of moles is equal to, of course, M divided by big M. It's obviously equal to 40 divided by the 74 that we just calculated. Okay? And then that's going to equal, of course, 0.54 mole. So now we've got the number of moles of the substance. I'm going to write it on top here, 0.54 moles. Okay. Now what we need to obviously do is we got to calculate what is the number of moles of ammonia that was produced. Let's keep that as X. Okay. And let's just cordon this off here because I don't want this interfering in my actual solution. Okay. Let's drop a little line here as well. So we've got calcium hydroxide, CaOH, 2 ammonia. So the mole ratio is 1:2. And over here we've got 0.54 that we calculated is to X. Okay? We don't know what this actual amount is. Alright? So theoretically, what do? We come down here and we say, well, 0.54 divided by 1 multiplied by the 2. Okay, is going to give you what X is equal to. Right? Therefore, X, which is going to be the amount of moles of ammonia that was produced from this reaction, alright, is going to be about 1.08 moles. Okay, now that I've got this, okay, what I'm going to do down here is I'm going to say, well, there's a formula, another formula for calculating the mole is V divided by Vm. Okay, now I've got 1.08 is the number of moles. The volume is 21 divided, sorry, not 21, sorry, let me take that away. The 21 decimeter cube set was, it is found that only 21 decimeters cubed of pure ammonia was produced. So what we have to do is we're actually calculating what should we have gotten theoretically. So 22.4, and up here, therefore, the volume that we should have gotten with this mole ratio of ammonia should have been produced only about 24.2 decimeters cubed. Okay. So therefore the volume of ammonia gas, which theoretically should have been produced, was 24,2 decimeters cubed. Now if we come here and we want to calculate the percentage yield, which is the formula, of course, actual over theoretical. So we take our actual volume, which was 21 decimeters cubed, divided by the 24,2, which was our theoretical yield, multiply that by 100. Therefore, the percentage yield should be about 86,8%. So instead of yielding 100% volume output, it only yielded about 86,8%, which is still a fairly decent output percentage-wise. Okay, so that's what we're actually calculating when it comes to percentage yield. What did we actually get divided by what we should have gotten? But sometimes we have to calculate first what we should have gotten. So using the mole ratios here and calculating the amount of moles of one substance and then using the mole ratio to see the amount of moles that should have been produced, okay, we end up with getting a volume that we should have gotten for ammonia to be 24,2, but we actually only got 21. That was our actual yield. And then we worked it out, 21 divided by 24,2 times 100 to give the percentage yield of the reaction. And that right there, grade 11s, is my presentation for this evening session. Thank you so much for joining me, and we will chat to each other next week, Wednesday. We will proceed to close this section and move into some exam practice.